So last time we had a look at why and how air moves, and we used the example of a sea breeze. Now let's have a look at how air moves and why air moves on a global scale. So we've seen already in previous lectures that on a global scale you get differences in heating. Because of the angle of the sun and the curvature of the earth, you get more heating at the equator. At the poles, the sun's rays are spread out over a wider area, and you get, plus other reasons, you get cooler temperatures. Okay, so if that was the case, then what we would end up with is air moving from the equator to the poles. It would just move, but would just be moving from the equator to the North Pole. If our system of air rising, moving out, and falling just gave us that big convection cell from the equator to the pole. But it doesn't quite happen that way. What we actually have is this system of three cells. Now, the reason is because as the air rises from the equator and moves up and starts to cool, it doesn't make it all the way to the poles because eventually the wind is bent due to Coriolis and will move directly east or west. And so it catches up on itself, eventually cools and will start to fall down. Okay, so you end up with this cell near the equator with rising air and circling air between about the equator and 30 degrees north and south. Similar thing happens at the poles, where cold air descends at the North Pole and South Pole. It moves out, eventually due to Coriolis, starts to move directly east and west, not north and south anymore, and starts to warm up relative to what it was and starts to rise, and you end up with this little convection cell going from 90 degrees north and 90 degrees south to again about 60 degrees. So here you have two cells. What happens in the middle? Well, sort of what happens in the middle, it's not driven by temperature differences, this cell in the middle, this convection cell in the middle. It's like a cog in a set of gears that the air is moving in response to the air around it, and you end up with this. You can see there the patterns there as air rises at the pole 30 degrees away from the pole and falls 30 degrees away from the equator, and that creates also a convection cell in the middle there. And so we end up with this system of three different cells, and we call these different cells, we give them different names. The one at the equator is called a Hadley cell. The one at the pole is called, not surprisingly, the polar cell, and the one in the middle is called the Ferrel cell. And so what we can then also see is the differences in air pressure on a global scale. Remember, rising air gives us low pressure and falling air will give us high pressure. Don't fall into the trap of thinking low pressure is cold and high pressure is warm. It's not. It actually has very little to do. It actually has nothing. Air pressure isn't affected, or you can't correlate air pressure with temperature in a local place. So just remember that rising air is low pressure and falling air is high pressure. Now, where are the areas of low pressure? Well, the main one is at the equator. So air is rising at the equator, and as that air rises, what is it going to take up with it? It's going to take up, in addition to the air, any moisture that's in the air, and it's going to then cool. And what happens when air cools? We looked at the hydrological cycle, you remember way back? Well, as the air cools, it will condense and fall as rain. And where are the main tropical rainforests around the world? Well, they're at the equator. Air that is falling gives us high pressure. Now, as that air is falling, it means you've got more air close to the Earth's surface. So it's not getting an opportunity to rise into the atmosphere and cool and fall as rain. Plus, as the air is falling, it's come from one of those convection cells where the air has risen and it's already rained, so the air is likely to be very, very dry as well. So where those convection cells meet and fall, you have areas of high pressure. And if you have a look at that, 30 degrees north and 30 degrees south of the equator, here you have the world's bands of desert regions, one right over Australia. So that's one reason why Australia is a very dry continent, because we just happen to exist under this area of very high pressure. The other areas of very high pressure, where are they? They're at the poles. And as you've probably heard, that Australia is the driest habitable continent, whereas actually Antarctica is even drier. Yes, it's full of frozen ice, but it never snows, or very rarely actually snows there. Why? Because it's another area of very, very high pressure.
Now, because the pattern of these pressure cells around the globe is driven by the sun, they don't stay in the same place throughout the year. The sun appears to move overhead throughout the year to us, and that's what gives us the seasons. So as the sun moves south during summer, so too will those bands of pressure cells. And as the sun moves north, giving us our winter, then those pressure cells will seem to move north as well. So if you have a look at this diagram here, this is the pattern of pressure cells that we've been looking at, let's say during an equinox, where the sun is directly overhead at the equator, giving us our pattern of low, high pressure cells. Now, if we move into summer, then as the sun moves south, as we saw when we looked at seasons, that will also cause those pressure cells to move south. So that's why in summer we have a band of low pressure cells across our north, giving us our tropical rainy season in the Northern Territory and north of Queensland and northern Western Australia. And we have a band of high pressure cells across the southern part of the continent. That's why we have much drier conditions during summer in the southern part of the continent. We now move to our winter, and those pressure cells move north, and then what that does is bring up the band of low pressure cells that were to the south of the continent, closer to the continent. And so we have, generally speaking, wetter conditions in the southern part of the continent during winter, and we have our dry season in the northern part, in the tropical regions of the continent.
Okay, so that's the basic principles underpinning our major bands of high and low pressure cells around the world.